Okay, and just briefly, for those of you who aren't familiar with Minibems, I think most attendees have an idea of what we're about by now, but essentially we're about heat network performance. And we have developed a specialized Internet of Things IoT-based system for optimizing, managing, metering and billing heat networks. And the unique proposition includes complete optimization of the whole system using real-time flow control, which delivers annual flow rate reductions of over 60% to deliver the same heat. This results in 25 to 50% gas or primary fuel savings. And additionally, the Minibems IoT controller enables remote triage and management of problems, reducing callouts by 60% or more. So we're managing the energy, we're managing the reliability of the heat network in conjunction with maintenance and also metering and billing. Okay, so good. So now we're going to move on to the main beef. This is going to be about how we look at how to integrate software into the design and management of heat network performance. So most of you seem to have a good level of software. So it'll be interesting to hear your thoughts about how you approach, how you do things. But in the meantime, I shall let Chris take it away from here, and we'll look forward to having the Q&A afterwards. Thanks, Chris.
Thanks, Ben. Good morning, everybody. Thanks for joining, and thanks also to Ben and the Minibems team for giving me the chance to talk to you today. So I'm going to talk about data, specifically how digital modeling and simulation tools can be used to deliver low carbon, low energy heat networks. Have you got my slides there, Ben? There we go. All right. So in preparing for today, really, I thought it'd be interesting to take a look at really how some of the market drivers are changing right now, and what the opportunities these create for digital tools and data in the heat network sector. So I'll explain a bit more about really what digital network twins are, and I'll hopefully walk you through an example of how we've used it in the past to really optimize design. Next slide, please, Ben. So just briefly about Hystopt. Hystopt is a software company, and we're all about optimizing the performance of HVAC systems and district heat networks, really to improve the efficiency, reduce the carbon emissions and lower energy costs from installations, both new build and existing. We're actually a spin-off from the University of Antwerp in Belgium, where we're based. But we also operate here in the UK, as well as in the Netherlands and Denmark as well. And we'll get into the software a bit more later on, but very, very briefly, effectively, it's a design tool and a simulation tool. So it allows engineers to do all their static load calculations accurately, but more importantly, allows the design then to be simulated against real life situations. So you can start to understand the thermal and hydraulic behavior of that system before it's actually built. And then you can start to really measure things like energy cost and carbon emissions and stuff really accurately against a real life profile. Next slide, please, Ben. So yeah, we do quite a lot of work. I've been to work with a range of different market sectors, healthcare, education, also a lot increasingly in the UK in the district heating market, be that citywide schemes or smaller communal schemes. We're doing quite a lot of work with universities at the minute, particularly where they're looking to figure out how they move their sort of centralized central plant heating networks from fossil fuel based through to low carbon solutions in sort of medium term. Most universities have a sort of 2030 net zero carbon target to hit, so they're quite motivated right now to figure out how they can transition from fossil fuel to heat pumps effectively. And also do quite a lot of work with housing developers, housing associations, to help them on both the design of new heat network systems and also to help troubleshoot and optimize existing installations as well. So as you'll see as we go through, the Hystopt approach really is all about finding that balance and trade-off between energy consumption and CO2 emissions, which we want to be as low as possible. Of course, we want investment costs to be as low as possible as well, but you want the comfort levels of the system to be as high as possible. So it's all about providing transparency and the ability to kind of make those value judgments on the performance of a system. How well does it perform from a comfort point of view, from an energy point of view, and what does that mean from an investment cost perspective? The other thing, just to kind of mention really, is recently Hysopt was awarded the Product Innovation of the Year at the City Building Performance Awards. Obviously something we're quite proud of, but the point of mentioning it really is about one of the reasons that it won is because we showed a very close synergy between the forthcoming update to the City Heat Networks Code of Practice and what Hysopt does. So we'll explain that a bit later on as we get into the presentation. Next slide, please, Ben. So just briefly, I think it's just worth touching on where we are in the market right now. There's lots of external influences going on. From an investment point of view, we've obviously had the HNIP, the Heat Network Investment Project, running for some time, and there was a further announcement just in the budget recently about another 270 million for a low carbon heat networks fund as well. So thick end of 600 million going into the heat network sector. We've seen from a legislation point of view the announcement of a Scottish Heat Networks Bill, and further to that we have the Future Home Standard, where it's talking about decarbonising all heating systems in the new build going forwards from 2025. Lots of changes around building regulations. I was actually reading about SAP 10 in detail yesterday, and some really interesting things in there about how that's going to affect heat networks. So lots of things going on that are going to affect our market. Next slide, please, Ben. I think the really interesting thing now is the BEIS heat network framework, which essentially is going to bring regulation into the heat network sector. It's going to really require owners and heat suppliers to demonstrate compliance with technical standards, both for new and existing installations. Everything's going to have to be certified, so Ofgem are going to have to certify every scheme, and not only new installations have to meet these technical standards, which will also include carbon compliance standards, for example, but also on an ongoing basis, all of these heat networks will have to provide reporting and transparency around consumer pricing, quality of service, and indeed how those systems are performing at a carbon level as well. So a lot more scrutiny and a lot more regulation coming into the market, and Ofgem will have the teeth to actually enforce this as well. So big change to the market that we know today. Next slide, please, Ben. The other thing, of course, that we're seeing in more broad terms is the general decarbonisation of heat, particularly as our electricity network decarbonises and we start to move towards electrification of heat as one of the primary drivers going forward. So we've seen the heat networks be on this transitional journey from second, third, fourth generation heat networks over time, continually reducing temperatures in those systems. It's pretty common now for a lot of new heat networks to be designed around 70-degree flow temperature, for example, or even lower. And we're now starting to see also very low temperature systems, ambient loop systems, we call them, where actually the temperatures are between 5 and 20 degrees, and then local boosting of those temperatures in the buildings using heat pumps. So we're on this kind of low carbon journey, and I think low carbon heat networks are certainly going to have a big part to play in future heat strategy in the UK. Next slide, please, Ben. So if we kind of boil all that down, I think the really important things for new heat networks and existing heat networks to demonstrate going forward are going to be three things. First of all, technical compliance. Is that network actually complying with all of the regulatory standards that are out there? Most likely CIBSE CP 1.2, but how do you demonstrate that compliance? Second of all, quality assurance. And what we mean by that really is predominantly around price transparency for consumers. How, as a heat network operator, am I delivering the lowest possible heat costs that I can, and how do I rank against other heat networks? Because that's going to become visible. There's going to be a league table of heat network costs. And then thirdly, decarbonisation and the ability for those heat networks to deliver low carbon performance both at the design stage and also on an ongoing basis, how do you demonstrate that? How do you prove that? So those to me are the key things. If you could just hit the button a couple of times, Ben, or just once. So this is, sorry, could you go back a sec? There we are. So to us, this means two things. It means bringing transparency about, first of all, making the right choices about your technology and your network design at the design stage, and throughout not only the concept design, but right away through to detail design. But also, how do you ensure and protect the integrity of that design into the installation, commissioning, and handover phase? How do you make sure the as-designed system is actually the as-built system as well? So when you get to certification and ongoing compliance, you know that the installation that you've designed actually is working properly. Thanks, Ben. Next slide. And if we look back look at where we are now and look back in the past, the problems we've had with heat network performance have all started around the way those systems are designed and developed. And yeah, I think these issues have been discussed quite a lot in previous Minibems webinars as well. So for us, there's a number of key things. Firstly, incorrect sizing and unknown partial load behavior of the system. So traditional approaches tend to be based around peak, static load, and rules of thumb for sizing, and it just results in systems that are oversized and just perform poorly under partial load conditions. So what this means is that not only are the capital costs of that system higher than they actually need to be, but more importantly, the poor performance of that network on a partial load basis means high return temperatures, high heat losses, and all that impacts on energy costs and CO2 emissions going forwards. Second issue is we're getting increasing complexity now. So in the past, HVAC systems or even heat networks were fossil fuel boilers and pumps, and that was really it. Now we're seeing heat pumps, CHPs, thermal storage, heat from waste, all sorts of combinations of different heat sources, all of which perform differently under different conditions and different temperature regimes. So how do you best integrate all those things together to get them to work properly? And with increasing complexity comes increasing sensitivity to correct hydraulic design. So you need to get that right and understand how it's going to perform at the design stage. Moving on then from design into sort of delivery, the other major area we see an issue with is component selection. So the correct selection of pumps and valves in a large complex system is very much an iterative process, all due to the interdependency of one component over another. And actually for large systems, this can require hundreds of thousands, if not millions of calculations that need to be done, which are just never done, obviously, sort of manually, select the pumps and select the valve authorities and so on correctly. So all this is time consuming, too complicated, and again, people use rules of thumb. So even if you sized your system correctly in the first place, the correct selection of all the valves and pumps and that is absolutely crucial to getting the whole thing working economically and efficiently. And then finally, commissioning. I probably don't need to say too much here, but yeah, over reliance on trial and error, commissioning squeezed into a very short time frame at the end of a project, all really leads to poor performance at the end of the day. Next slide, please, Ben. So this is really where digital design tools and data start to come into play. So as I mentioned before, HiSopt is a combination of both a design tool and a simulation tool. So you can see in the little model that's been created here on the screen, it looks a little bit like a 2D CAD image. In fact, what's sat behind that representation of the design is a mathematical model of the physical installation, which really understands how the system functions from both a hydraulic and a thermal point of view. So, for example, it knows and understands all the temperatures, the flow rates, the behavior of all the system components, the generation equipment, the efficiencies of the boilers in the plant, and so on, across the entire installation. So, as a design tool, first of all, these sorts of products automate the necessary engineering static load calculations to help the engineer produce an optimal design. So, for example, calculation of flow rate, pipe sizing, valve selection, pump selection, taking out a lot of the rules of thumb and the manual errors that come into that design process. But the real value comes in when we then start to add building load data, occupancy profiles, weather data, so that static model, and we can then use this to simulate the dynamic behavior of the system. So by doing this, we can really start to see how the system behaves under partial load conditions. So what happens to the flow rates and the system temperatures when under part load, and how do the components and the generation plant react to those partial load conditions, which are changing all the time. So when we actually run a simulation, what we do is we actually run that building against 30-second simulation steps over the course of an entire heating season. And then we can start to assess by looking at the outputs from the model, you know, what and quantify the performance of the system. So what's the energy consumption? What's the carbon emissions? What's the comfort, and so on? And actually, how then can I start to look at the system design and see where I've got high return temperatures, for example, and then how can I eliminate those hydraulically to reduce energy costs, carbon emissions, and so on. And it also allows us then to compare actually different design concepts as well. So, you know, you might end up with 3 or 4 different concept designs of how your heat pump system is going to connect into your heat network, and you can actually simulate all of those and see which one works best. The other thing about these models is that they're all cloud-based, so which has loads of advantages. First of all, the computing power needed to run these simulations, but actually from a practical point of view, the ability for the model to be shared with different stakeholders in the supply chain. So, for example, the model made at Reba Stage 2 can be passed to the consultant who's doing design for Stage 3 and Stage 4. That design can be refined, passed on to the contractor who can do the component selection, and so on and so on and so on, and even into the commissioning stage as well. So the model lives with the whole design process. Next slide, please, Ben. So what I want to show you quickly is a case study of how this has been used. This is an energy center design. So all the things I'm going to show you, they work at an energy center level, they work at large heat network level, they work at the building level as well. But this is just an example of an energy center concept design that was produced for a heat network. It's a 5 megawatt energy center, and the goal really was to integrate heat pumps, CHP, and gas boilers, and really to minimize the use of boilers and maximize the use of heat pumps and CHP to get the best combination of lowest carbon, but also lowest running costs through getting the CHP to run as well, which obviously is a bit of a dichotomy now. So next slide, please, Ben. So the first little model on here is a representation in our software of the consultant's Reba Stage 2 design. So what you can see, I've forgotten I can't point things out. So what you can see at the bottom left-hand corner there is a 450 kilowatt water source heat pump. Above that you have a 1 megawatt CHP engine. And then at the top there you have an array of gas boilers. It's just put as one boiler in here, but it's about 5 megawatts of gas boilers. And we have some thermal storage on that system as well. And we can see on the right-hand side of the screen the kind of metrics. When we run a simulation, we can see the metrics that the simulation tells us about. So we can see that the boiler has about 47% thermal energy share, working at about 89% efficiency. We can see all the gas consumption and so on. We can see the CHP has about a 49% thermal share as well. And obviously that's being used to generate electrical power at the same time. And our heat pump is really not doing anything much at all, about 5% of the overall thermal share. Seasonal COP of about 3.2. And at the bottom we can see all the energy costs. So then the total energy cost is about £200,000 per year, and carbon emissions of about 3,500 tons. Next slide, please, Ben. So what we then ran through are a number of hydraulic optimization iterations just to see the impact of different hydraulic concepts. So the first one really was just splitting out the thermal energy storage into separate storage for the CHP and the heat pump. And we can see on the right hand side what that means. It doesn't really change the boiler share so much. And actually what ends up happening is we get the heat pump to run more often, which is great from a carbon point of view, but actually that's at the detriment of the CHP engine. So has an impact positively for CO2, but actually has a detrimental impact on the overall annual energy costs. You can see energy costs go up by about 18,000 a year, and the CO2 goes down by about 3%. If you can flip to the next slide, please, Ben. So we've then looked at other options. Again, different hydraulic integrations of the plant, and you can see the impacts that has. Now we're really starting to increase the heat pump share to about 18%. We're reducing the boiler share down to less than 30%. We've made about a 23% saving in energy costs and an 11% saving in carbon as well. We haven't changed boilers, it's the same plant. All we've done is change the way they're hydraulically linked together. You could skip through a couple of slides, Ben, just in the interest of time. There we go. So this is kind of the final iteration of that concept design, really, where we've made further hydraulic changes to the way everything's linked together. So we've got the heat pumps now running connected to the return flow of the primary side. We've changed the connection between the CHP and the boilers as well. And now you can see on the right-hand side there the overall impact. So ultimately, reducing the annual energy costs against that initial design by about 67%, 68%. 26% in carbon emissions. You can see we've got the CHP doing about 70% of the load, the heat pump doing around 30% of the load, and a small amount of top up needed from the boiler. So we've got a much better balanced, more optimized design. It's going to reduce the energy costs for the client, and the chances are there's going to be capital cost savings made as well in the sizing all that pipe work for the whole system. Next, Ben. Next slide, please, Ben. If you skip on past this one, because we're running a little short of time. So, gone the wrong way. There we go. So, in a nutshell, we talked about technical compliance and quality assurance and low carbon. Using digital tools like this just shows exactly how you can start to get insights into the transparency of the calculations and ensuring that the metrics you're comparing against for technical compliance, be they carbon or anything else, are met. And also how a design can be optimized to lock in the lowest energy cost at the design stage with much more transparency about how that system's really going to perform in real life. And the same goes for carbon as well. How can I use those assets to make sure they're hydraulically and thermally connected in the right way to deliver low carbon? So definitely helps you make all the right choices at the design stage. Next slide, please, Ben. Obviously, the key also, though, is about, click on, please, one, Ben. The key is also about how do I then ensure the integrity of that design at the installation and commissioning and handover stage. So without going into too much detail, effectively, the software also then, once the design is correct, iteratively does all the calculations necessary to select all of the pumps and valves in the system based on the correct valve authorities, the correct pump heads for lowest possible energy cost of that system. So it helps with component selection, and actually it helps with commissioning, because as part of the same outputs, not only does the installer get a shopping list of equipment that he needs for every single component, but also what the preset commissioning value should be for those parts as well. So every valve, the installer knows how that should be, what kV value or KVS value that should be set to. So he can actually pre-commission that system as part of the installation. So not only does it work correctly, but actually it saves them a lot of time on site as well. Next slide, please, Ben. So I talked a little bit at the beginning just about how about the changes to CP 1.2, and one of the key things in there is this idea of evidence pack. So the idea there is a report, or it's actually a lot of spreadsheets that follow the design process for the heat network. There are, for each stage, there's a prescriptive set of evidence information that's needed within the annexes to CP 1.2, and effectively the HISOP digital twin of an installation or design provides that evidence pack. All of the technical information that's needed as part of that evidence pack is already in the digital model. So as the model follows along through the design process, it takes all that information with it, and the vast majority of the information needed for that evidence pack is already in the digital twin. So it's a really good way of demonstrating compliance. And that's one of the things that the judges of the CIBSE Award were really, really pleased to see. Next slide, please, Ben. So we talked a lot about the technical side of things. We've done over 150 projects with HiSOPT to date, and the key things that we kind of find, certainly from a financial point of view, are that by reducing redundancy, reducing plant sizing and so on, we're able to actually take capital cost out of systems, but also from an operation cost point of view, between 30 and actually 50% annual energy cost reductions are possible. Where we're looking at existing schemes of CHP, the CHPs generally don't run very well. Hydraulically, we can change those systems, and it's not uncommon for us to get 40, 50% or even higher annual energy cost savings as a result of getting those CHP engines to run for a lot longer during the year, and really fast paybacks as well. We've talked about all the operational and environmental side benefits already. Last slide, please, Ben. So yeah, we've kind of hopefully given you a bit of a hint there about how digital design tools can really help with securing technical compliance schemes, underpinning the quality assurance side of things, and also making sure that systems deliver low carbon performance as well. We've talked a bit about how traditional sizing and approaches to design are really challenging for modern complex systems with lots of different heat generation and different temperature regimes, and effectively how heat network digital twins bring transparency of all that at the design stage. They help the process be managed all the way through the complete process from design into handover, and really unlock those objective comparisons around financial performance, operational performance, and environmental as well. So thanks very much for listening. If anyone is interested in a bit more about this, we do have a couple of webinars coming up in June, which I think Ben's going to share the information with you later on. So yeah, thank you very much.
Nice one. Thanks very much, Chris. Fantastic. Yeah, so the things I'm getting out of there are that, there's some serious legislation and regulation coming down the line that heat network owners of all shapes and sizes are going to have visibility of and pay attention to, and there's the technical issues that essentially companies such as HiSOPT and Minibems are trying to address to the way heat networks have been designed or how they operate today. So we're trying to improve future heat networks, but also existing heat networks. So I guess just one thing I wanted to know was, given that we're both in the data sector and we're both trying to use data to improve things, what sort of data does HiSOPT need from heat network owners, operators, and how do you use that data? So from a purely practical point of view, to kind of make a model, effectively what we're doing is taking the hydraulic schematic, the P&ID of a system, and we're digitizing that and putting it into the digital model. So that's the first thing we use is that digital twin. That allows us to, so that P&ID allows us to make the drawing, if you like, but to be able to really run those simulations for existing systems. What we tend to use is half-hourly metering data for the course of the year, and then we can load match the model that we've created against the last year's operational data, so we can be sure that the way that the network or the design is performing replicates real life really well, and we usually get that within 2 or 3% plus or minus. And then what that means is we know that as we start to build in or look at different iterations or optimizations, our benchmark is starting from a really good place. So yes, really P&IDs and then metering data. Gotcha. And I mean, given that we're both in the data world, and there's a lot of, it's a big trend, isn't it? You leveraging data to improve all sorts of energy systems. I mean, how would two companies such as ours interact and complement each other then?
Well, I think there's two parts to that. I think one, clearly, where HiSOP sits is very much a theoretical model. So it sits in the design stage, or it sits outside of what we're not doing is taking in real life data in real time. We're kind of using a snapshot of data and then being able to model something in theory and look at how you can improve things on an iterative basis.
Yeah.
Where Minibems sits is in that operational phase, in that real-time data. So I think the synergy really is to be able to compare through a Minibems system what's actually happening, but have an idea from the HiSOP model of what good actually looks like. So you have, a benchmark. How close are you to actually achieving that optimum? And of course, the weather data and occupancy profiles of what's happening in the building on a day-to-day basis will be slightly different to what was modeled in the system. And I think the other really important one is, this is all about showing the benefits of lower return temperatures back onto the system, really. So it's being able to model the improvements to the return temperatures that Minibems is able to deliver as well, really. So having that data injected into the theoretical modelling is also a really important part of the exercise.
Gotcha. Finn, did you want to step in, and do you have any comments or thoughts?
Yeah. So I suppose how I see HiSOP being really valuable is what you said, Chris, around the 30-second interval kind of snapshot of the real-time performance, obviously modeled performance of the building, and seeing how being able to model how buildings really operate under partial load. Obviously, when buildings are designed, we're always talking about that peak load design is what everyone is designing to currently, and I suppose what you have the capability to demonstrate is the impact of that design as soon as load drops away, which is 99% of the year, isn't it? And how Minibems fits with that is that we're controlling to that partial load, so we're able to kind of match what your model would do in the best case scenario. So whatever you control strategies you might implement on a heat network in a theoretical model to deal with partial load, we can implement with our control loops run at 2-second intervals. So we are continuously updating valve position, pump speeds according to real-time conditions. So we can modulate right down to very, very small loads essentially, and maintain heat transfer, maintain return temperatures. So really match what you're doing in the model with reality. Yeah.
And it was interesting that you mentioned the generations of heat networks that have been developed. And I know that we're both involved on the retrofit side of things in terms of improving existing heat networks, but has there been any talk or any discussion or any experience of transitioning a heat network from a 3rd generation and turning it into a 4th generation heat network or something along those lines?
I mentioned at the start, we're doing a lot of work, as it happens with the university sector, but they tend to be campuses with lots of buildings hanging off what they call district heating, and it is, I guess. I think they're motivated to get on with that decarbonisation faster than residential systems, mainly because they've all set themselves, they're all very competitive, and they all want to make sure they beat their nearest neighbour to net zero carbon. So it's not uncommon for universities to have a 2030 or 2025 net zero carbon target, which is hugely ambitious, I think. But we're working with a number of universities where they've typically got already investment in large scale CHP and gas boiler systems, and looking how on earth do we transition this stuff to, likely as not, heat pumps. And that starts with the buildings. How do you make those buildings low temperature ready? And then how do we optimize, what impact does all that have on the return temperatures and the delta T's across the distribution network? And then how much more do we need to do to make that network suitable for use with heat pumps? And then how do we plan the integration of heat pumps? It's unlikely they're going to rip everything out and put heat pumps in instead of CHP. There'll be a gradual transition. But using tools like HiSOP allows them to have that kind of long-term view. They can model the first steps and what impact that has and how to do it properly, but we're mindful of what their end goal is and what their ultimate solution is going to be. So yeah, we've got a few. There's also we're working with a hospital where they wanted to do a zero carbon building demonstration. It's a standalone building, 25-year-old boilers, chillers that are completely trashed. They were mindful to put very, very expensive air source heat pump system in, which to my mind was a little bit the wrong solution to begin with. Not because air source, just the way they were doing it was questionable. But what we showed them was that actually the carbon savings and the energy cost savings that heat pump would make for them, because it wasn't a complete solution, it was a partial solution, that they could actually make the same level of savings and carbon savings with a fraction of that investment just by optimizing what we already had. This is not even about changing the old boilers. They weren't even condensing boilers. They're old, non-condensing boilers, but just changing the hydraulics would give them the savings that the heat pump system was going to make. So, it's about actually working with what you've got to optimize that first before you start throwing very expensive kit at a system.
I think that's often the case.
That's very interesting. Yeah, the focus is always on the generation, but actually, what needs addressing in buildings and what we see as a business is that most systems are 30, 40, at best 50% efficient, and there's a lot of opportunity to, for significant optimization before you even think about changing the source of heat. Yeah.
I think the other thing that's interesting is when we transition towards lower temperatures, which of course you're going to need to do to bring in low carbon technologies. Actually, we can take advantage of all the historical oversizing of pipework that's gone on, because you can use that to really, if you optimize the buildings and the operation of the system, you can actually deliver the right amount of thermal power in the oversized pipework at lower temperatures. So we need to be able to use that for advantage.
Which concurs with our experience, which is that we can take an old radiator system that was designed ostensibly on 8271 and operate it for most of the year on an average radiator temperature of 50-55 degrees and still heat the building.
Exactly.
And significantly reduce your flow and return temperatures as a consequence. Yeah, for most of the year. Yeah.
Okay. Nice one, Chris. Thank you very much. That was great. Hopefully we'll welcome back Finn back shortly as well. We've got some questions from the audience. Thanks for those. We'll get to them in a moment. So the big thing I'm sort of taking away from this is that we've got Scottish Heat Networks bill that we saw last week, that the Westminster government's doing legislation as well. So we've got some big regulation and legislation drivers that are going to push us towards getting these things as tight as possible. And we've also got not just new heat networks and big new heat networks that we need to try and achieve, but also existing heat networks that we need to improve. And this sort of data-driven approach and this sort of level of detail that you can put together with the HISOP software can help provide insight there. I mean, this is a sort of very broad question, but is there any what sort of specific data are you looking for from heat network owners and operators such that they can, take advantage of HISOP?
So I think the kind of key things we need to create a model in the first place, Ben, be that a new build or indeed an existing installation, is a schematic. So what we're doing essentially is taking the hydraulic schematic of an installation and we're digitizing it. So we create a model. So that creates the physical model of what the system is. But in order to run the simulations, we need the consumption data from the building. So meter data, the kind of data that Minibems provides, for example, in terms of consumption and metering and monitoring. So the more data we've got about how the system is currently performing, we feed all that into the model. So then we run a simulation. Our starting point is not only what's physically in the plant room in the old building, but how that's worked over the last year or 2 years or whatever. And then when we start to run iterations and modifications to that system, when we simulate those, we know that benchmark is starting from a good place.
Okie dokie, sorry. I think you just froze there for a moment and then my phone went off. Sorry about that. I've got another question, but Finn, do you want to pop in anything at this point?
No, I think go through the questions that you've got there.
Yes.
Yeah.
Fine. I mean, just the other thing that I wanted to ask was, you know, we've both got data. How does our software and data interact and complement each other, Chris?
Good question, Ben. I think obviously what we've talked about today, and HiSOP really is a theoretical model. Okay, so it's used in either design stage or taking a step back from, you know, modeling an existing installation and looking at how performance can theoretically be improved. Okay, but of course, and we talked a little bit in there also about how you translate a good design into good practice as well, the commissioning reports and the component selection, that sort of stuff. But obviously, it's very important then to continually monitor how that system is improving in real life. We don't take in live real-time data, and that's really something that Minibems does very, very well. And the question we get asked a lot is, well, you know, how do I continually monitor that the model I've made in the HiSOP environment, how is that performing in real life? And the question is, the answer is that's really hard to do actually, because the assumptions we make about weather data and occupancy data and so on, building loads are all based on historical information really, and those variables change in the real world over time going forwards. So it is really important to have, you know, not only the design optimized, but also continually monitoring that, which is really where the likes of Minibems comes in, because but that gives you a benchmark also when you're looking at your live stream data to understand what good looks like. Yeah. And that's one of the problems with maybe looking at just operational data alone. You don't actually know what good looks like, or how close to optimum you are, whichever way you want to look at it.
Yeah.
I would add to that, Chris, that you know, I thought was interesting about your presentation is that, and your software, is that you're able to demonstrate what partial load looks like, and I think that's a really the key advancement against kind of SIBC or, you know, traditional design methods. Obviously, to date, pretty much everybody's just designing for Christmas Day, you know, your -4, your -7 condition. But what you're able to do with your software is, I presume, using degree day data, simulate the partial load operation of systems over the whole year. And I suppose where Minibems comes into that is that Minibems is able to operate flexibly at partial load, is able to optimize, you know, control to partial loads, whereas traditional heat networks and valves, etc., really just only control to the design load, basically. So yeah, there's a lot of symbiosis there essentially between the two. But the key difference obviously is Minibems is implementing. It's not just monitoring; it is implementing the actual real-time control according to the control parameters that you want that system to operate to. So you're designed to operate to. Yeah.
Okay. Listen, I'll bring in. So in the order that they came in, Catherine Cooper, thanks very much for this. A few comments here, but the first question was, has HiSOP initiated any projects to help mothballed biomass plants get back into productive use? We all a wry reaction there, yeah.
Have we helped to mothball biomass? I'd love to, but no, not yet. In all seriousness, so I mentioned at the beginning of the presentation that some of the projects we're working on at the moment in the UK are driven by a lot of the universities who have got fossil fuel-based heat network systems, you know, and a lot of the universities have zero carbon targets, 2030, 2035, and are looking at how they transition those effectively high temperature fossil fuel based systems away to low temperature heat pump based systems really. That all starts with optimizing the buildings that are hanging off the network so they can operate at lower temperatures. One of the things we can do is one of the benefits of everything being oversized and size on static loads is that usually the pipe works too big. So it does allow you actually to, if you optimize the hydraulics, to actually increase the temperature spread on that network and start to run those at lower temperatures as well. So we can start to use the benefits of, or the advantage of some of those pipeworks being oversized. So yes, it's absolutely, there's a lot of projects we're looking at right now that are looking at transitioning from high temperature fossil fuel based systems to low temperature heat pump based systems.
Just to go back to the biomass point, yeah, I mean, it is a terrible shame that there's a huge amount of stranded biomass assets out there. Either failed installations or never commissioned in the first place. I think really it is a problem that we can address as Minibems. Your problem generally is, again, high return temperatures or very, very poor delta T's, leading to biomass boilers coming on and off, cycling on and off far too frequently, far too frequent parts wear and failure. All of that is addressed by getting your return temperatures down and your flow rates down, and getting good run times on boilers, both run times and off time, so you're not cycling plant all the time. So certainly something we would be keen to get involved with.
And certainly by the same token, I perhaps misunderstood the question a little bit, but yeah, we do a lot of schemes like that with hospitals, actually, with CHP, where the CHPs are in and they just never run, or they run for a fraction of what they're able to do really, or designed to do. And that's all, as you said, also to do with flow rates and return temperatures. And whenever we look at a CHP scheme, we know that we're going to be able to reduce the energy costs for that customer by between 30 and 50% just by getting the CHP to run more often. And that's all about hydraulics. It's all about the hydraulic connection and interconnectivity between the CHP and the boilers. So the same thing applies to biomass, I think.
Good stuff. I'm going to group together 3 questions here regarding HiSOPT's features, if you like. So from Tony Amos, thanks for this question. So the first one is, I'll shoot them out to you, Chris, and then you can respond to all 3. Does HiSOPT software include ground loop design when optimizing heat pump outputs? Alistair Moore asks, are your calculations models at HiSOPT covered by any indemnity insurance? And Ken Neal asks, previous presenter, hi Ken, does HiSOPT keep a library of product information that is fed into calculations? How do you collect this information? So it's ground loops design, heat pump design, indemnity insurance, and your product information library.
Okay, that's fine. So, thanks, Tony, for that question. Ground loop design, absolutely. So, the way HiSOPT has developed around closed loop and open loop borehole systems is really about enabling engineers to calculate and simulate the energy balance of those systems, particularly where you have heating and cooling. So you have heat rejection and heat extraction. And as I know you know very well, Tony, it's all about that long-term energy balance and making sure you don't over-extract or over reject back into that aquifer or borehole. So things like the thermal conductivity and the temperature of water, those are all inputs into the software. But absolutely, the hydraulic design of the heat exchange and the simulation of how that energy storage medium reacts over 10 years, 20 years is absolutely something that we simulate in the software. I'll be happy to take you through that separately because it's quite an interesting area. Alistair, thanks for that question as well about indemnity. It's always a tricky one. At the end of the day, HiSOPT really is about providing transparency to the designer about how their system works. So, like any other tool, really the indemnity of the designs that are put forward are the responsibility of the consultant engineer, the person using the software. Obviously, from a product liability, we have all that covered off, but the professional indemnity side ultimately is the responsibility of the designer using the software. What we're giving them are insights into how the system is going to perform versus other concepts or other designs that he's putting forward. So yeah, that's the answer to that one. And in answer to Ken's question about the kind of library, yes, there's an entire we call it an inspiration library of pre-configured, pre-designed plant rooms and configurations, particularly when you start getting into combinations of heat pumps and CHPs and boilers and other things. So there's a whole raft of pre-designed templates that can be used, and we also have manufacturers' equipment in our software as well. So when, for example, you run the component selection element of the software to choose the pumps and the valves and the boilers and the plant, you can choose to do that either on the generic level, or you can do it on a brand specific level as well. So for example, we have pump manufacturers, we have HLU manufacturers, we have boiler manufacturers, lots of valve manufacturers have their products in our software already. So if a contractor or supplier has a particular preference for a particular brand, they can run the product selection using that particular brand.
Okay, got a couple more comments, but one specific design question comes from John Mitchinson. Thank you very much, John. Should the exterior design temperature of -4 degrees be revised upwards, that given that climate models predict warmer outside temperatures, thereby avoid oversizing of the system?
I didn't quite. What was the actual question in there, Ben? I didn't quite catch the beginning of that.
Yeah, sorry. So John's asking whether the exterior design temperature of -4 degrees should be revised upwards because we're expecting to have warmer winters essentially.
That's probably more of an opinion. I don't know if you want to tackle that one as well, Finn. I think you kind of still have to account for those extreme events, don't you? We had the beast from the east, not a couple of years ago. So I still think we're still going to get extreme events. I think the key to it though is understanding how these systems operate at partial load as well as full load, and that's the key, right? The way we design systems now is based on just that extreme weather condition, whereas software like Hysopt and Minibems is providing insight into how those systems perform under partial load conditions, so you can perhaps change your control strategy. It's having those insights allow you to design systems that operate better under partial load, not just designed for full load.
Yeah, I would agree. I think you still have to account for the -4 condition, well, whatever the design external temperature is for the area that you're in at the moment. But yeah, the problem is that you don't want to you want a control strategy and implementation that means that you're not operating at that all year round, which is how most buildings operate today. When the system turns on, they're operating as if it was -4. You need a system that allows that modulates according to real-time conditions.
Yeah, and what we typically see is where systems are designed to give a return temperature at 60 degrees at the -4 condition. Actually, what happens is as the thermal power requirement of the system goes down, the return temperatures go up, and that's where you get inefficiency, and that can be dealt with by controls and hydraulics, as Finn just said. So.
Certainly, one of the things that we're seeing is we continue to see, and I think everybody knows it, is continual oversizing of plant. I think we've got baked in margins of error that go into design, especially using kind of SIBC methodology. There's often over engineering that goes on, and I suppose with your system, Chris, you can really optimize that selection in the first place, so you don't get that oversizing going on. Certainly at Minibems, our data is indicating that loads are typically very, very a lot smaller than has been designed for, and over time we expect to be able to feed that data back out into the industry in the form of diversity curves and diversity data to show how a typical apartment block might use heating and hot water. in real terms.
Exactly that. And I think, you know, when we model existing systems, the first thing we generally find, based on the meter data that we extract, is that the peak thermal loads are massively overestimated in the first place. But the advantage is that if all the pipework is sized to take those overestimated thermal loads, we can actually use that to drive the temperature regimes right down. So in a retrofit situation, there's actually an opportunity to be able to make systems work more efficiently just by understanding, you know, how low can we drive those flow and return temperatures, how much can we increase the delta T and still deliver the right level of comfort into those properties, given that the pipe work that's in there is a fixed variable.
Yeah, that concurs with what we do as well. So, you know, we often find we can reduce average radiator temperatures by 20 degrees and still heat properties for most of the year. Yeah, exactly. So take advantage of that initial oversizing that's gone on in the first place. Yeah.
Okay. I think a big word that's coming out of that is that the typical way to approach design is based on essentially rules and predictions, whereas what we're trying to do is actually just get the heating system to function in real time based on real time conditions, and that's where the future is. It's actually being able to respond very quickly to that. That's our time up today. There's a couple comments that Catherine Cooper put through that I'd like just to share with you all. And one is that the design community really needs to access operational data to validate models. And Catherine suggests that we lobby the Scottish Government to pay for systems like this to be installed as part of a quality assurance compliance. The condition being that if you access funding, you share data. And Catherine also suggests that we can look to the chemical and food industries to benchmark these sorts of requirements. There's a final technical question that Catherine asks. Surely the design temperature gets set by the degree day data. Is there an answer to that?
I don't know, actually. I mean, I just had a table that I've used for years now, which is depending where you are in the country, there's a design outside temperature that you should be designing heating systems to. I forget the source, to be honest, but I don't know whether that's derived from degree day data. Yeah.
So I mean, I think the answer is yes, it is, but then it's how the building actually works, which is all about having responsive systems and softwares and strategies in place. I'm going to just finish up. Thanks so much for your questions, and thanks for that, Chris.